In these videos I want to do something practical and concrete, namely to give us some practice with the Dirac notation. And I will do this in the context when this is completely equivalent to dealing with vectors. In here I'm first going to have a look at vector products. So all possible ways that you can multiply vectors. And then I look at eigenvalues and eigenvectors. And in both cases I'm going to do it with normal vector notation. And then I'm going to look at these things also using the Dirac notation. So this is still focused on the mathematics of this, but then I will translate this into a physical context by considering discrete quantum systems. So these are really the most simplest quantum systems one can think of. And I will focus on two examples, the so-called two-level system and a periodic discrete system. And both of these terms I'm going to explain when we come to them. And I selected these examples because they are also serving as a nice preparation for material that we will see later in this course. So even though this is optional, this is not even very stretching. Okay, so let's look at some ways that we can multiply vectors. And I will start with real vectors in 3 dimensions. So let us just consider 2 of these, a vector v and a vector w. So these are just 2 examples. And let us multiply these vectors with themselves using the dot product. So the dot product of v with itself would be 2 squared plus minus 2 squared plus 1 squared, which is 4 plus 4 plus 1, which is 9, and therefore 3 squared. And the dot product of w with itself is 3 squared plus 2 squared plus 6 squared, which is 9 plus 4 plus 36, or 49, and therefore 7 squared. And I selected them not completely at random, because this is also the squared length of these vectors. And just for simplicity, I took vectors for which the length is an integer. So for instance, we can use this to normalize the vectors. Let's denote the normalized vectors with a hat or caret, and that would be just dividing the vectors by their length. So that would be 1 over 3 times the vector that we had initially. And we can do the same, creating a so-called unit vector for w. And that would be 1 over 7 times the vector that we started out with. So next we can take the dot product between the 2 different vectors. So these are real vectors, and we just use the normal dot product, just multiplying all the components at the equivalent positions, which equals 8. So these 2 vectors are actually not orthogonal to each other, but we could construct, for instance, an orthogonal vector which is orthogonal to v by just combining these in this way. So when we then demand that this dot product is equal to 0, then we can work this out using what we have worked out already. So here we have 8 plus alpha times 9 And therefore, when we set alpha equals to minus 8 divided by 9, then we obtain a vector which is orthogonal to V. So here we have done this concretely with numbers, but this can also be written in a more general form, and this helps us to introduce another product between vectors. For this, we solve this equation here just generally for alpha. So alpha then comes out to be the negative of the dot product between V and W divided by the dot product of V with itself. Next, we are going to reinterpret these dot products as matrix products between a row vector and a column vector. So this is mathematically just the same thing, but it is useful here because we can then write this also in the following form. And then we can insert this above into our definition of W prime. We can also express this in terms of the unit vectors, these vectors here. But in either way, what is useful to recognize is that this here can be interpreted as a matrix. And in doing so, it then makes sense to also use the identity matrix and to write this all in this form here. So what we have here is actually something that we can interpret as a new product, and we can call this the outer product. So the dot product is also sometimes called the inner product, and this would be our outer product. Above here we do this with the same vector, but this can also be done for two different vectors. And it's simply the matrix that you obtain in this way. And its matrix elements are just these products here. What we have done here geometrically has the interpretation of a projection, where this operator here projects W onto the component which is orthogonal to V. And it does so by just subtracting the component which is parallel to V. So this has a direct geometric interpretation, and in these definitions of the projection operators we can make use of this outer product. So here we interpret our result as a matrix, but there is a very similar product which is known as the Kronecker product, or also the closely related tensor product. And there we would just take these same components and interpret them as components of another vector. Let's call this vector u. And this vector has simply a more complex index. Maybe just think about this as numbers. Say if I would be running from 0 to 9 and j would be running from 0 to 9, you can just interpret this as a decimal number running from 0 to 99. So you would just get 100 different components of a long vector, which you just obtain from these vectors here by just combining the indices in this way. This can also be carried out from matrices, but here we are going to focus on vectors. Let us write this down concretely for our two vectors. So we have the vector v and the transpose of the vector w. And when we multiply this out, we multiply 2, minus 2, and 1 to the components of w. And they just really appear basically in the same order as in the vectors. So this gives you a matrix with entries 6, 4, 12, minus 6, minus 4, minus 12, 3, 2, 6. And then the tensor product would be taking all of these vectors and just putting them below each other. You could also do it with these vectors. There are two different conventions. These are called gradings, but we just take the simplest one. This tensor product or Kronecker product would then be denoted by this symbol here with a circle around a multiplication sign. And so this would now be a very long vector. With these components here. All of these products which I mentioned so far appear in some form in quantum mechanics. And there's of course one more very familiar product, the cross product. And we will indeed also encounter this, but not because we want to do quantum mechanics per se. We will encounter it because we also want to do quantum mechanics in 3 dimensions. For instance, when we introduce the angular momentum. And for this, we have this very striking pattern of making a cross to multiply components. Say for this one here, we have -2 times 6, and then we subtract 1 minus 2. And then we have 1 times 3 minus 2 times 6, and finally 2 times 2 minus -2 times 3. So these are all certain crosses that we can draw between these components. And then we can simply work this out, which gives us -14, -9, and 10. And the geometric interpretation of this is that this is a vector which is orthogonal both to v and w, which we can of course check using the dot product. Well, there is a very general rule that tells us that this vanishes, but we can of course work it out just concretely. So there we obtain -28 plus 18 plus 10, which is indeed 0. And we can do the same for w. So that would be -42 minus 18 plus 60, and this vanishes as well. Also, the cross product has its generalizations, but we will not need them. But just for fun, when you think about how it, for instance, features in Stokes' theorem, this can be generalized into the wedge product. And this forms the basis of exterior calculus, which is all about differential geometry. So this is the language of general relativity. But also it is very useful for electromagnetism, say in a curved space. And there you would then write down Maxwell equations as these equations here. This is very compact, so this tells you that this language is very powerful, but it is of course also very abstract, so I leave this here.